Welcome back everyone. In this lecture we will see some applications of Weyl character formula. First we will begin with the Coston multiplicity formula. For that purpose first we need to define what is called Coston partition function. So let's fix some notations. So recall what is this cone Q plus. So this Q plus is nothing but Z plus span of all simple roots alpha 1 etc. alpha n. So this is also same as Z plus span of the positive roots delta plus. So let us fix this notation. Delta plus is equal to beta 1 etc. beta n, where n is the number of positive roots. So now given this what one can do, one can define this function called costant partition function, costant partition function. So which is defined to be, let us call it P of mu for mu in Q. Okay. So this is defined to be the following number, again the number of tuples R1 etc. Rn, number of tuples R1 etc. Rn such that this mu is written as R1 beta 1 plus etc. Rn beta n. So of course these tuples comes from Z plus power n, and this makes sense only if mu is in this cone Q plus, or otherwise we define it to be 0. So it is defined to be 0 if mu is in Q plus, we define it to be this number of tuples R1 etc. Rn such that mu is equal to R1 beta 1 plus etc. Rn beta n, otherwise we just define it to be 0. Note that, so what it actually counts, the P of mu in a more plain language, this actually counts the number of ways we can express mu as sum of positive roots. So basically for mu in Q, so the P of mu counts the number of ways we can express mu as a sum of positive roots. And of course by this definition, when mu is not in Q plus, P of mu becomes 0. So now it is an elementary exercise that if you take the Verma module for any given lambda in H star, so the multiplicity of the muth weight space, that is the dimension, is given by the partition function on lambda minus mu. Okay. And this is true for any lambda in H star and mu in H star. So I will leave it as exercise because this is just comes from the definition. So now let us state the multiplicity formula. So here is the Coston multiplicity formula. So let us call it theorem. So this is due to Coston. So let lambda coming from the dominant weight lattice, sorry, set of dominant weights lambda plus, and mu coming from the weight lattice. So then what we are interested in? We are interested in the multiplicity of mu in V of lambda. So that means the number m mu lambda. So which is by definition the dimension of V of lambda mu, and this is given very explicitly by the following formula. You take sum over sigma in W such that the sign of sigma times the partition function of W lambda plus rho minus mu plus rho. So this is very explicit closed formula for the multiplicity, and of course in practice this will be very difficult to compute. So you can see that this partition function is only non-trivial whenever this W lambda plus rho is bigger than mu plus rho in the dominance order. Otherwise, this difference will not lie in Q plus. So, then this you can just assume to be 0. But in practice, you can actually see that the Weyl group indeed grows very big. Okay. So, for example, if you take type E8, it has some 62,000 plus elements. So, using this formula, constant formula, it will be very difficult to compute the multiplicity. And another drawback about this formula is alternating formula. So, the sign actually changes here. Okay. So, whenever you see some formula that has this alternating signs, so that is very bad formula in terms of combinatorics. Okay, so let us see how to prove this. This is indeed immediate application of Weyl character formula. So, let us set up the notation and then just rewrite the Weyl character formula, then we will get this. So, here is the proof. So, start with chi lambda. So, that is by definition summation m lambda mu e power mu, where mu comes from capital lambda. So, this is all just formal computations. Note that S rho inverse is nothing but e power minus rho 1 divided by product 1 minus e power minus alpha, alpha in delta plus, and recall 1 divided by 1 minus e power minus alpha is given by summation e power minus I alpha, I range from 0 to infinity. So, now if you take the products among all of them, then it is easy to see that you are just taking the product here. So, 1 divided by product 1 minus e power minus alpha, alpha in delta plus is nothing but the product summation e power minus I alpha, I range from 0 to infinity, where alpha runs over delta plus. So, that means, so this is going to be exactly equal to, if I fix some minus gamma, then this is going to be P of gamma, where gamma runs over Q plus. So, if you think about it, we are taking the product among all this summation. So, if you fix gamma, then you want to write that gamma in terms of this sum of positive roots, and the number of ways you write, that will be the coefficient of this this e power minus gamma in this product. So, in particularly if we use this explicit expression of the inverse of S rho in the character formula, then the character formula says chi lambda is given by S lambda plus rho divided by S rho. So, that means this is exactly equal to summation sine of sigma e power w lambda plus rho and mixing signs. So, it should be sigma here. So, sigma in w, then that sigma should appear here. So, then you can see that this summation sigma in w e power sigma w lambda plus rho, that is going to be exactly S lambda plus rho. So, this times, so you want to have this S rho inverse, which is given by e power minus rho times this 1 divided by product 1 minus e power minus alpha. So, which gives you exactly that summation P of gamma e power minus gamma plus rho, where gamma runs over Q plus. So, now you can make this gamma to run over Q, there is no issue. Then if you rewrite this on the left hand side, you have the multiplicity of mu in lambda e power mu in capital lambda is equal to summation. So, you can just run over gamma and then see what happens. So, this is exactly equal to sine sigma. So, let us run over gamma summation sigma in w e power sigma lambda plus rho minus gamma plus rho. So, this is the multiplicity, the P of gamma should be here. So, now if mu is equal to the sigma lambda plus rho minus gamma plus rho, so then you can easily see that from this expression, this gamma is going to be sigma lambda plus rho minus mu plus rho. So, if you substitute it back, so you can see that the right hand side becomes summation gamma summation sigma in W sin sigma P of sigma lambda plus rho minus mu plus rho times e power mu comes. So, this is going to be our coefficient of e power mu on the right side. So, we are changing the variable mu to like gamma to sigma. So, we are changing the variable gamma to mu. If you do this change of variable, then we are rewriting all these things. So, then this is exactly equal to summation mu in lambda, the multiplicity of mu in V lambda e power mu. So, this implies that the multiplicity mu in V lambda is given by summation sigma in W sin sigma P of sigma lambda plus rho minus mu plus rho. So, this is a very explicit and straightforward application of Weyl character formula. So, now even though like this is very explicit closed formula, okay, the practical difficulties are this Weyl group is indeed large and this function is somewhat very hard to compute because this demands lots of informations. Okay. So, now let us actually move forward and then I will prove now Steinberg's formula. So, that is again some immediate application of this Weyl character formula. So, recall what is the Steinberg's formula. So, this actually gives the number of V lambda that occurs inside tensor product V lambda 1 tensor V lambda 2. So, it gives the very explicit formula for that multiplicity. So, the Steinberg's formula, so let us actually write it down. So, this is given by, so given lambda 1 lambda 2 in dominant and lambda again dominant. So, we are interested in the number of times V of lambda occurs inside V lambda 1 tensor V lambda 2. So, this is actually we want to count what is this number. So, this number is given very explicitly by this double sum. You sum over sigma and then sum over tau and then you take sine of sigma tau times the constant partition function applied on these elements sigma lambda 1 plus rho plus tau lambda plus 2 rho minus lambda plus 2 rho. So, again same practical difficulties are there in using this Steinberg's formula. The Weyl group will be very large and this is indeed alternating sum and computing this constant partition function is also very hard actually. So, let us prove this. So, this is just obtained again by using this Weyl character formula and rewriting things in some clever ways. Okay. So, here is the proof. So, let us go through the proof. Just write chi lambda 1 times chi lambda 2 to be summation n of lambda chi lambda where lambda runs over lambda plus. Okay. So, just write like this. So, now we are interested in computing n of lambda in terms of the Weyl group. So, now what we will do first we will multiply. So, we multiply by S row on both sides. So, then we get the following. So, you keep for example, the second term and then you just change the things. Okay. So, we keep just second term. So, in particularly chi lambda 1 is given by summation the multiplicity mu in lambda 1 e power mu in capital lambda. So, we are going to just use this formula for the first term. The second term by multiplying by S row it becomes S lambda 2 plus rho. So, this becomes chi lambda 1 S lambda 2 plus rho is equal to summation n of lambda S lambda plus rho, where lambda runs over lambda plus. So, in this we are going to use this explicit expression of chi lambda 1 and then rewrite things. So, now we also use this constant formula for the multiplicity. So, if you use that what will happen to the left hand side. So, let us work out the left hand side. So, the left hand side becomes using this constant constant formula. So, constant formulas for the multiplicity. So, we write chi lambda 1 as this summation mu lambda 1 e power mu and then replace this mu lambda 1 using the constant formula. So, if we do that, then what we get on the left hand side is exactly equal to summation mu in lambda summation sigma in w sine of sigma the partition function p of sigma lambda 1 plus rho minus mu plus rho. So, this is what is there in the constant formula times you get this e power mu, because this is exactly the. So, this part is what the multiplicity. So, then times e power mu you get and then we will keep that S lambda 2 plus rho as it is. So, now we can again use the definition of S lambda 2 plus rho. So, that is given by summation the sine of tau runs over w e power tau lambda 2 plus rho. So, if we just use this, so then we get the above formula. So, the left hand side becomes again summation mu in lambda summation sigma in w. Now, there will be another sum over tau in w, because that is coming from this S lambda 2 plus rho. So, then we keep the constant partition function as it is. This sine tau times sine sigma, because sine is being group homomorphism, this becomes sine of sigma tau, then times this partition function sigma lambda 1 plus rho minus mu plus rho will stay as it is, and then times e power mu plus tau of lambda plus 2 rho will be there. So, this is what there on the left hand side. So, now we can actually simplify this left hand side by substituting the variables. Okay. So, we want to replace this variable by, let us say, some mu dash. So, let us replace that by mu. Okay. So, then it just changes as follows. So, what we are going to do? We are going to actually, so maybe like I will just write it as gamma plus rho, no issue. So, what we will do? We just write, so this is the change of variable that we are doing, mu plus tau lambda 2 plus rho. So, this you write it as gamma plus rho. So, then it is clear that what will be this minus mu plus rho, because that is what appearing here. So, this also should be rewritten. So, then you can easily see that minus mu plus rho is exactly equal to tau lambda 2 plus rho minus gamma plus 2 rho. So, this is what you get on the right side. So, if you substitute, then the left hand side becomes summation, now gamma runs over lambda, summation sigma in W, summation tau in W, sine of sigma tau, then the partition sigma lambda 1 plus rho plus tau lambda 2 plus rho minus this gamma plus 2 rho comes times e power gamma comes. So, this is the term that you are getting on the left hand side. Now, we need to look at what we get it on the right hand side. So, the right hand side is nothing but this summation n of lambda s lambda plus rho. Now, what we can do, we can again use the expression of s lambda plus rho and then rewrite what is there on the right hand side. So, let us try to do it slowly. So, the right hand side becomes, the right hand side is nothing but summation n of lambda s lambda plus rho, lambda runs over lambda plus. So, now what we do, we just simply rewrite this using this s lambda plus rho, which is given by summation sigma in W sine sigma e power sigma lambda plus rho. So, if you use this, then this can be rewritten as follows: summation lambda in lambda plus summation sigma in W, then sine of sigma n of lambda e power sigma lambda plus rho. So, this is what we get if you just replace s lambda plus rho here. So, now what we are going to do, we are going to change the variable. So, we use this change of variable. So, write this sigma lambda plus rho as some gamma plus rho. So, then it is clear that lambda plus rho is nothing but sigma inverse gamma plus rho. So, using this, if you rewrite, then the right hand side actually becomes summation lambda in lambda plus summation sigma in W sine of sigma. So, again we have to replace lambda. So, lambda becomes sigma inverse gamma plus rho minus rho. So, we just use that n of sigma inverse gamma plus rho minus rho here, then times e power gamma plus rho we get. So, now we have to see where this gammas are running. Okay. Here the lambda is indeed running over capital lambda plus, and since lambda plus rho will be just dominant somewhere, but we are using this while group action. So, we will be able to reach all elements in the weight lattice. So, that means this part indeed becomes gamma in capital lambda. Okay. So, this is what the right hand side looks like. But now this can be again massaged little bit, because sine of sigma is same as sine of sigma inverse. So, using that you can rewrite this as summation gamma in capital lambda summation sigma in W sine sigma n of sigma gamma plus rho minus rho e power gamma plus rho. So, that is because sine of sigma is same as sine of sigma inverse. So, that tells you that this is what the right hand side is. But now notice that whenever this n of sigma gamma plus rho minus rho is non-zero, that forces that the sigma gamma plus rho minus rho is indeed dominant weight. So, note that this n of sigma gamma plus rho minus rho is non-zero, that implies that the sigma gamma plus rho minus rho must be dominant. Let us go back to our left hand side. So, we have substituted mu plus tau of lambda 2 plus rho to be gamma plus rho. So, that means here this is what appears here. So, there is one rho is missing. So, we should write this rho here. So, now we have this left hand side that has some formula. So, the coefficient of e power gamma plus rho is given very explicitly by this. But what we are interested in? We are interested in the coefficient of e power gamma when gamma e power gamma plus rho when gamma is dominant, because that is how we can actually capture the elements this n of gamma. Okay. For example, if sigma is identity, then we get here this n of gamma. So, for gamma dominant, so if n of sigma gamma plus rho minus rho is non-zero, then that implies sigma gamma plus rho minus rho is again dominant. But for gamma being dominant, then that would imply that gamma plus rho is indeed what is called a regular element. So, gamma plus rho of h I is going to be positive for all I from 1 to n. So, using this in this situation, I will leave it as exercise. You can prove that sigma must be identity. So, now for gamma in lambda plus, if you compare the coefficient on both sides. So, one side there is no contribution. For gamma dominant, you have only this n of gamma as only coefficient on the right side. So, for gamma dominant, n of gamma is the coefficient of e power gamma plus rho on the right hand side. Okay. So, that becomes clear with this observation. When gamma is dominant and n of sigma gamma plus rho minus rho is non-zero, so that would force that sigma is identity. So, that is the coefficient that you are getting on the right hand side, which is n of gamma. So, that implies that what is the corresponding coefficient on the left hand side. So, that is what you see in the Steinberg's formula. So, that is exactly given by summation sigma in W, summation tau in W, sin of sigma tau, P of the partition function applied on the sigma lambda 1 plus rho plus tau of lambda 2 plus rho minus gamma plus 2 rho. So, this proves the formula. So, on the other hand, we get n of gamma to be equal to summation sigma tau varies over W, sin of sigma tau, the partition function correspond to sigma lambda 1 plus rho plus tau lambda 2 plus rho minus lambda plus 2 rho. So, this completes the proof of Steinberg's formula. So, I will stop here and we will continue with the Weyl dimension formula in the next class. Thank you.